Good day, I'm Norman Wildberger. In this video we want to talk about divisibility. In particular, looking at divisibility of biggish numbers. We want to move towards talking a little bit about primes and unique factorization and some problematic issues in that direction. Okay, so divisibility is, of course, somehow intimately connected with multiplication. So here's an example of the product of two natural numbers. Here's the number 111, and here's the number 11111. And its product is 1111111111111. Ordinarily, we would just say 3 times 5 equals 15 using our Hindu-Arabic shortcut notation for this thing. Now, I remind you that such a product is ultimately defined in terms of lots of products between the entries here. So to get this product, what we really do is we multiply each one of these with each one of those. So in particular, we can think about this as being, say, taking that first stroke there and multiplying it by each one of the strokes in the second box. That'll give us that collection there. And then if we do the same thing with the second stroke, well, we would get another collection of 5. And with the third stroke here, we would get another collection of 5. So if we look at it this way, we can see that this 3 times 5 is the sum of these smaller m sets of 5. So 3 times 5 is 5 plus 5 plus 5. And alternatively, we can look at it sort of from the other point of view. We can think about the products as being organized by taking the first one on the right-hand side and multiplying it by each one of these. So there's a product each of there, giving us that m set there. And then we repeat that for each one of these 5 in the second set, getting these 5 sets of 3, showing us that 3 times 5 is 3 plus 3 plus 3 plus 3 plus 3. So in each of these situations, we see that the multiplication can be viewed more simplistically as a kind of repeated addition. And when we say that 15 is divisible by, say, 5, another way of thinking about it is that it's writable as a certain number of copies of 5. So here's our definition of division, or more precisely of divisibility. So if n and m are natural numbers, let's say that m divides n, and we'll introduce this notation for that. So m with this long vertical bar n, that means m divides n, precisely when k times m equals n for some natural number k. In other words, when we can find a natural number k, so when we multiply by m, we get n. In such a case, we'll say that m divides n. So for example, up here, we could say that 5 divides 15, because 3 times 5 is 15. You could also say that 3 divides 15. Okay, so this is a very standard story. We want to talk a little bit about how this actually works, especially for bigger numbers today. All right, so for example, this number divides this number because, well, we can write this times this 3 as that. And one way of seeing that is that we can sort of peel off copies of this one here. So there's one copy, there's another one, there's another one, another one, another one, another one, another one. So we see that we have this many copies of this thing composing our number. In Hindu-Arabic form, we would say that 3 divides 21 because 7 times 3 is 21. As another example, 4 divides the empty m set, which is our 0. Since we can find a natural number that multiplies this 4 to give us the 0, namely the natural number 0. Right? So 0 times 4 is really a 0. Or we would say in our Hindu-Arabic, 4 divides 0, since 0 times 4 equals 0. I remind you that 0 is a natural number in this story, so we have to make sure that our definitions apply to it. Sometimes we have to pay a little bit of special attention to 0 because it's a little bit different sometimes. In particular, let's also have a look at the case of 0 dividing 0. So we claim that 0 does divide 0. Why? Because, well, if we just apply the definition, say 2 times 0 is 0. Right? That's how we multiply. 2 times 0 is 0. And so we can say that 0 divides 0 in Hindu Arabic because 2 times 0 equals 0. So notice that this is a little bit of a strange notation, right? Usually we don't think about 0 over 0 or the fraction 0 over 0. We're not really talking about a fraction now, okay? We're just talking about this divisibility of whether one thing can be expressed as a multiple of something else. And 0 can be expressed as a multiple of 0, so it makes sense for us to say that 0 actually does divide 0. That's consistent with our definition. So here's a theorem that summarizes some important basic facts about divisibility. So suppose we have three natural numbers, say k, m, and n. So if m divides n, then m divides k times n. If m divides k and m divides n, then m divides the sum k plus n. And if k divides m and m divides n, then k divides n. All right, so let me prove the first one for you, and I'll leave the other two as pleasant exercises for you. Okay, so the first one, we're assuming that m divides n, and we want to show that m divides k times n, where k is just some other natural number. So if m divides n, then what does it mean? Well, it means that L times m equals n for some other L. We used k before, but we are already using k, so let's use a different letter, say L. So m divides n means that we can find an L so that L times m equals n. That's what it means for m to divide n. All right, then what about this k? If we take this equation here and multiply both sides by k, k times L times m will then obviously be k times n. And then by rearranging and say eliminating the multiplications, just writing the juxtaposition instead, then we get kl times m equals kn. Now this kl is also a natural number because the product of two natural numbers is a natural number. And so we have the situation that this natural number times m equals kn, and so m divides kn. That's what we were trying to prove, that if m divides n, then it also divides k times n. Okay, so it's pleasant to write down proofs in this direction that demonstrate these other two laws. All right, so we have our definition of divisibility. Now what about a criterion or a method to determine whether one number divides another number? So to decide if, say, m divides n, one strategy is to successively subtract or remove copies of m from n until one of two things happens. If nothing remains, eventually, then m divides n. And if we get a remainder, say r, which is strictly positive, it's actually bigger than 0, but less than m, then m does not divide n. And notice that we're introducing this notation here that if we have the divisibility sign with a slash through it, then this means that m does not divide n. So for example, how about this thing here? Here's a natural number, and we're interested in, does it divide this natural number? Okay, so here's how we could do that. We could, and we're being sort of like primitive people here, maybe we don't even know how to count this far, okay? And we don't know the names for these things. We just want to know, does this primitive natural number divide this primitive natural number? So what we're going to do is we're going to take this number here, which I've copied down here, and I'm going to see if I can write it as a multiple of this thing. So what I'm going to do is subtract or take away copies of this. Okay, so the way I'm going to do that is sort of sequentially. So I'm going to sort of copy this thing here over here. So there's, well, I'm going to count, but I don't really have to count. 1, 2, 3, 4, 5, 6, 7. So I just find the first group there, that matches up with what I've got there. Okay. And then sort of stop there and start again. And now I match this next group up. I think over here. And then, so I'm sort of imagining subtracting this from the total, and then subtracting this from the total, and now subtracting another equal number. So that's 1, 2, 3, 4, 5, 6, 7. I am cheating a little bit by counting, but I don't have to count, I can just match up. And once I've done that, if I've done it correctly, I see that there are these two left over. Okay, so we have two left over after we've subtracted a bunch of these 7s. Okay, so the answer is no. This number does not divide that because we get a remainder which is not 0. And this is going back quite a ways to the Math Foundations 8 lecture where I first started talking about division and how to divide one number by another. That's really what we're doing here. Okay, so this idea that if we want to see if one number divides another, what we're really doing is we're subtracting that number repeatedly and seeing what kind of a remainder we get. And this is really effectively the same as long division. And let's have a reminder of how that goes, going back to that Math Foundations 8 video, with this sort of alternate way of doing long division, maybe a sort of simplified way that I proposed at that time. So if we want to divide, say, 2166 by 38, we're interested in whether 38 divides 2166. So our strategy is to divide, and we're going to do that by subtracting multiples of 38 from this. Okay, so there's a bit of judgment here, and it's not necessary to do this in only one way. So we're going to take 38 and have a look at this and say, well, we could maybe fit 40 copies of that in here. So 40 times 38, make that multiplication, is 1520. Which good is less than this? So we're going to take 40 copies of 38 away. So we do the subtraction, we get 646. And now we ask how many 38s will fit inside 646. Well, we don't have to be too accurate, and let's say we want to do relatively simple arithmetic, so we can say, well, 10. 20 is not going to work, but 10 will. So let's subtract 10 38s. When we do that, we get 266. And how many of these fit inside there? Well, maybe 6 of them. 6 times 38 is 228. When we subtract that, we get 38. So we see that there's one more that we can subtract for a final remainder of 0. So we're successively subtracting multiples of 38 and keeping track of the number of multiples that we've subtracted, as well as the remaining total at any given time, until eventually we try to get as close as we can to 0. In this case, we get all the way to 0, and then we can count up that the total number of 38s that we subtracted was 57. So what we've seen here is that the original number, 2166, is 57 times 38 plus a remainder of 0. There's the remainder. Now, of course, we don't always have to get a remainder of 0. That might have been a remainder of 4. If there was a 4 remaining there, we would replace the 0 with a 4. But in this case, there is a 0 remainder there, and so we can say that yes, 38 does divide 2166. Now, I'm aware that many students these days don't learn long division in school anymore, which is a bit unfortunate. And it's true, though, that the standard procedure for doing long division is a little bit complicated. It's quite involved. And I think this procedure that I'm outlining here is a little bit simpler. It's more forgiving. You can make less than optimal choices and still end up naturally with the right result at the end. So let's have another example. Here's a question: does 571 divide 34,098? So to answer that, we'll divide 34,098 by 571. So we're going to ask how many of these can fit into there. And we want to do it in a simple kind of way, so maybe we'll start with 50. Because 5 times 5 is 25, which is sufficiently under 34 as to be sort of on the safe side. So 50 times this, well, there's a 0 there, and then we multiply by 5. So we get 5, 35, 28. And that is less than this, which is good. So when we subtract, we get this number 5548. Now, how many of these fit into there? Well, not quite 10. 10 would be too many, so let's err on the safe side and say 8. Then 8 times this is 8654, which is less than this. And so when we subtract, we get 980. And now we see that we can subtract one more. So we could have subtracted 9 at that stage, but it doesn't matter if we just take another step. Then we subtract another 571 to get, I think, 409 as a result. So what we can conclude here is that the total number of 571s that we subtracted was 59. We subtracted 59 copies of 571 from our original. So our original 34,098 is 59 times 571 plus this remainder of 409. Now this remainder is bigger than 0, but it's less than 571. So we're not in a position to subtract yet another 571. This is already less than 571, so we're not obliged to do anything more. The procedure is finished, and we can definitely say that this thing is not divisible by 571. So 571 does not divide this because of this remainder that's obtained here. All right, so let's look at a bigger example. How about, does this number divide this number? So we definitely shifted gears here to go from natural numbers to numerals, to Hindu-Arabic numerals, right? Because these are numbers that are now getting so big that, well, we could actually still write them down as natural numbers, but maybe it's nicer for us to think in terms of the number or the Hindu-Arabic framework. In any case, this number is well, there's the hundreds and thousands and millions, so this is 250 million and something like that. And this here's zeros and thousands and millions and billions and trillions. So this is 609 trillion and so on. Okay, so does this number divide this number? We could do this by long division. We could. But my computer is much faster at it. And the way I get my computer to figure out whether there's a division here is to ask it to calculate this number mod this number here. Okay, so there's this operation called the mod operation that my computer knows about. And if I ask my computer what is this, it will spit out this number here. And what this means is this is the remainder after we divide this number by this number, we get a remainder. Okay, and the remainder is, in this case, 243,315,666. Telling us that, in fact, the answer to the original question is no. This does not divide this, because if it did, then the remainder would be 0. Here is the technical definition of the mod function. This will be quite important for us. So the definition of n mod m equals r, say. It means that if we divide n by m, the remainder is r. So technically that means that n equals k times m plus r for some natural number k, and such that this remainder is between 0 and possibly 0 up to but not including m. Another way of saying that is that if you divide n by m, then the remainder is r. That's the easy way of saying what this means. N mod m equals r means that the remainder when you divide n by m is r. So here we took this big number mod the small number. We got the remainder that you get when you divide the big number by the small number. So make sure that you absorb this definition, very important definition, going back to the great German mathematician Carl Friedrich Gauss, whom we'll talk about more next time. All right, so let's up the ante a little bit and move to some bigger numbers. Let's ask, does 13 divide 8 to the 8 plus 5 to the 5th? So notice that this is still in the realm of natural numbers, but it's expressed now using some mathematical expression. these towers of exponents. We could write this out as a natural number, very onerous, but as a Hindu-Arabic numeral, it wouldn't be that bad. Okay, so I'm going to ask my computer to do this, and the way I do that is I write down 8 to the 8 plus 5 to the 5 mod 13, and I ask it to evaluate that, to tell me what is the remainder if I divide this by 13. And it does so instantaneously. It says that the answer is 6. So I know that if I divide this number by 13, I get 6. So the answer to the original question is no. 13 does not divide 8 to the 8 plus 5 to the 5. All right, let's jack things up a little bit further and ask a similar kind of question. Does 13 divide 8 to the 81 plus 5 to the 54? Okay, now we're getting to numbers which are definitely pushing the bounds in terms of writing out a natural number expression for them. But in fact, we could still write out a Hindu-Arabic form for them. Not that difficult to do that if we have our computer to help us. So does my computer respond pleasantly? Yes, it does. So my computer will deal with this very quickly. It will tell me that the result of taking this number mod 13 is 7. In other words, the remainder that I get when I divide this number by 13, the remainder is 7. So that means that the answer here is no. 13 does not divide this. Now notice that this mod formulation of things circumvents a key part of the earlier calculation in the long division. If we actually divided this number by 13 using a long division, we would end up getting that this is equal to some multiple of 13 plus 7. So this is the k that would be the sum of all the multiples of 13 that we've subtracted. Right? We're going to have to subtract a lot of multiples of 13 from this to get something down to 7. Right? So this is going to be some huge number. And doing this by hand would be hugely onerous. And even asking the computer to do this, I mean, the computer can do this, but this number k that it will generate will be a very, very long number, and it won't be expressible in such a nice fashion like this. I'll just get some string of Hindu-Arabic digits, quite a lot of them. But since I'm not really interested in that in terms of this problem, I'm only interested in whether 13 divides this number, and for that I'm really only interested in the remainder. So this mod notation, this mod concept, does exactly what we wanted to do here. It tells us what the remainder is without expressly calculating the quotient k. It's a very clever kind of idea, going back to Gauss. All right, so let's keep going. Let's ask a tougher question. Does 13 divide z? Z is 10 triangle 10 plus 23, our favorite reasonably big number. Does 13 divide z? Well, what do you reckon? Well, the chances are about 1 in 13, actually, aren't they? Because every 13th number is divisible by 13. So if I kind of just pick a random number, chances are 1 in 13 that it's actually divisible by 13. So since I've kind of just picked this randomly, I would say there's a 1 out of 13 chance. The z, this 10 triangle 10, is of course this thing here. It's this tower of 10s, 10 to the 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 10 plus 23. And so we want our computer to evaluate this number mod 13. So I've put this into my computer and I've pressed evaluate. And what does it do? This is what it does. It does nothing. It just sits there. It doesn't know what to do about this, because this number is too big for it to convert into its usual format, say as an ordinary Hindu-Arabic number. It can deal with Hindu-Arabic numbers which are hundreds or thousands of digits long. That's no problem. But unfortunately, this is not just hundreds or thousands of digits long. It's much, much longer than that. And my computer cannot deal with it directly in that fashion. So, what are we going to do? Are we just going to throw up our hands and say, well, we can't compute this? Well, in fact, we can compute this. and I'm going to leave it to you as an exercise. All right, so exercise, find this remainder. And you don't need to know any modular arithmetic. All what you need to do is do a little bit of experimentation and think about this problem. So a high school student will be able to answer this question as long as they're willing to make some investigation, let's say. Okay, so you have to investigate things. But you should be able to, with some thought perhaps, to calculate this remainder. In any case, what we're interested in is exploring technology like this to be able to check divisibility for bigger numbers. Okay, so we want to understand how to check divisibility even if both of these numbers are, say, very big. So in order to do that, we need to understand more deeply this lovely mod operation. Okay, so we have to connect with Carl Friedrich Gauss, and this is really a key innovation that very important in modern cryptography, very, very useful and important technologies to be able to deal with this modular arithmetic. So that's what we're going to be doing next time. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.